Hi everyone, and thank you for attending my presentation. My name is Yannick Segman. I'm from Maya HTT, and today we'll be discussing electromechanical collaboration for board-level thermal analysis, so an integrated approach for design optimization. So let's start with a few market trends. So the growth in electronics has caused a few trends in this digital era to emerge. Devices are getting smaller, so the different market calls for ever smaller, lighter, and more powerful products with more functionality. Also, if you look at disruptive pull of electronics in mature industries, so nowadays key differentiator in new products are coming more and more from the electronics and software compared to the mechanical aspect of the product. And also, if we look at the two last trends, so customer experience is essential to growth, and customized and personal products on the rise, well, you can just think of the Internet of Things, sensors. Electronics is impacting every aspect of our lives. So, with this increased dependency on embedded electronics, we have a need for better collaboration tools between the different design domains. So, electronics, mechanical, and simulation. So, the important question is what is the cost of a disconnected design process between electronics, mechanical, and computer aided engineering, so simulation? A recent survey showed that 50% of companies require at least one additional design iterations to address electromechanical issues. So obviously the cost is dependent on the market and the type of products, but you can think that an additional design iteration means at least more resources put on the product and delayed time to market. And also, nearly 70% of corporations cite electronics, mechanical, and simulation design synchronization as a significant product design challenge. So, we'll go through those different challenges a bit more in detail shortly. But first, let's have a quick look at the agenda. So, we'll start by the challenges for an efficient ECAD MCAD CAE collaboration. Then, after the presentation, will be divided in two aspects. First one, ECAD MCAD integration. So we'll discuss the importance of choosing the right data format and how to minimize design iterations. And then after we'll switch to CAD CAE integration, where we'll look at how to optimize a thermal simulation workflow as well as a structural simulation workflow. Now, just a quick note on Maya HTT. Maya is a software development and engineering consultancy firm. So for well over 30 years, we've been a strategic partner with Siemens Digital Industry Software, developing 35 plus software solutions for the portfolio, so can't even keep the count there. But in addition, we also provide services and design, manufacturing, simulation, PLM. We can do custom development, workflow automation, and we also have experience in IoT, AI, and big data deployment for our customers. So first, let's have a look at the challenges faced by the engineering teams. So on the left, you have the ECAD domain, where the schematic is designed, PCB layout is done. In the middle, you have the mechanical domain, which takes care of all the 3D information for the components, the board, the enclosure, making sure that all clearances are fine. And on the left, you have the simulation aspect. So here we listed a few possible options: electronics cooling, PCB thermal, vibration and acoustic. What's interesting is that sometimes when you start, for example, with electronics cooling, then after you may need to go in more details. So going from a system level analysis to a board level analysis to then a component thermal analysis. Also, it's possible that if we look, for example, at the solder creep pin's durability, you may require inputs from other simulation results. So for example, the electronic system cooling and the durability will be required. And once the multiphysics aspect is completed, you need to be able to send back this information to the mechanical designer, even to the electrical designer, if changes are required in order to optimize your design. So when looking at all these multiple arrows and this workflow, you realize that there's a few pain points that are present. So first of all, multiple physics are involved, right? So you really require high-end technologies. Also, there's file transfer involved here between ECAD and MCAD, between MCAD and CAE, and also between the simulation. So very often those processes are taking too long and the data files to exchange or transfer are too large. As I mentioned a little bit previously, you might need multiple outputs to be used, so multiple applications may need to be used in order to achieve this digital twin and be able to optimize your electronics design. And the fourth one, well, multiple applications mean that multiple stakeholders may be involved in this process. So you may need these different expertise just to be able to use the tools, and also you might need to share this data across the different departments in an efficient manner. So let's start with the ECAD-MCAD integration section. So to understand a little bit better which file format we should be using, I think it's important to have a quick review of what is a printed circuit board. So a PCB is a structure used to connect and support electronic components. It's made of multiple laminates, which include mostly glass epoxy-based material, and then you have copper that's coated on both sides. So the end-plane connections for the components are done by etching away the copper to leave the different traces. And then after you can protect them with either plating if they're pads or with solder mask for the traces. The true plane connectivity is done by drilling holes either mechanically or by laser, and then by adding copper within the barrel. So you have the traces, that's external, internal, the copper planes. You have the stack-up details that you need to fully understand with the file format. So dielectric thickness, the signal layer thickness, the adhesives, and obviously the vias for the interconnections. So are you just using through hole vias? Are you using blind buried vias? So vias that don't go directly through the board? Micro vias, which would be smaller in this case. So all these aspects are very important. So if we look at the different formats available out there, there's at least two of them that are very good. So the first one is ODB++. So if you're doing thermal analysis today, you might already be familiar with that format. So it's a format that allows you to capture all the details of the PCB from the component to the board, the stack-up details, the vias. So this format contains everything since it's a manufacturing format. So it's used by the ECAD designer to send to the PCB manufacturer to fabricate the PCB. Now, the IDX format, which is a collaboration format, also contains the same information. But what's interesting is that you also have a workflow feature that is completely unique with regards to the other file formats. So what is the IDX collaboration format? So the IDX collaboration format, it's a workflow for incremental design transaction. So when you start the design collaboration, you initially send the full design, which we call the baseline. If it's coming from the mechanical side, you can put your initial board dimension, initial connector, LED placement, some mounting holes. But then after, the design will advance concurrently. So any following changes will come from an incremental IDX file, for which the receiving end can either accept or reject the changes. So it's really like a discussion going on here where you understand the changes that are coming, so you have a robust transmission, you have a visualization of the results of the changes that are being done, and everyone can synchronize on the changes at the end. Now, one thing that can become difficult sometimes is managing all those changes. So there's a lot of back and forth, accepting, rejecting changes. Sometimes the discussion and collaboration can take longer. And sometimes a rejection can be caused by something very simple that is just unknown to the initial designer or to one of the domain. So one of the questions when it comes to IDX collaboration like this is how can we minimize the number of iterations? And the optimized workflow that we're presenting, there's one new feature that we developed and are tooled, which is ECAD design rule checks inside the mechanical tool. DRC rules is a concept that's already used on the electronic side, so you can check clearances between traces, holes, components. But on the mechanical side, most of the time what you have in your tool is a generic 3D clearance tool. And what we did in our side to optimize the workflow is to enable the 2D rules to come from the ECAD side. So what we do is that we pre-process the data to allow orthogonal checks in the X and Y plane and not just the 3D clearance checks. And what's very important when you use a design rule checks and a mechanical tool is to support multiple PCB concepts to define those rules more easily. The body for the board substrate, the areas, the component board side, the ref desk, package, part number, all those concepts need to be understood. And obviously the performance is very important. For example, for 3D clearance checks, 2000 components, double-sided board took around 10 seconds. So if you take too long for doing those checks, then it might become more easy to simply send an incremental change to the other domain and get their feedback. But if you can get quick response from a DRC checks when you're doing what-if analysis, moving things around, it's very valuable. And then obviously you need to be able to differentiate between the PCB entities and the assembly component to conduct more advanced types of checking when it comes to the PCB, to the mechanical enclosures, for example. So by combining the IDX collaboration workflow with the design rule check engine, we really get an optimized ECAD-MCAD collaboration process. At the top here, you can see that you can preview the changes, send the transactions between the two domains, and you get a synchronization of data, which is often difficult to guarantee with other formats. And again, you minimize the number of iterations. You make those transactions more efficient with the design rule check engine because each domain can make sure or do initial validation to see if those changes, what they're proposing, make sense or not, if they violate any rules that would be from the other domain. So by combining the IDX and the DRC capability, you really make sure that the transactions you're doing are more meaningful like this. Now let's continue with the thermal simulation of PCBs. We've mentioned it a little bit earlier in the presentation. The miniaturization aspect of electronic is very important in the different industries. And then you combine that with the increase of performance that is required, and then it becomes more and more important to cool the electronics correctly because the heat can have effect on the circuit operation as well as on the PCB integrity. So for example, on the thermal effects for the circuit operation, the gain, threshold voltage, leakage, and other electrical parameters can vary with temperature. As for an example, if you take a 10 degrees Celsius temperature increase, it can double the current leakage in active devices. And obviously the PCB integrity is also very important. All materials expand and contract depending on their coefficient of thermal expansion, in other words the CTE. So the temperature increase may lead to component failure, or as we can see in this picture, from a via cracking within the PCB, which can be very difficult actually to catch when you're testing your board. The importance of a good CAD-CE integration here is required for proper electronics cooling. So we're going to look at two aspects of the MCAD-CE collaboration. First, how can we promote the collaboration between the designers and the simulation experts? And then, how can we use the simulation capability earlier in the design process? So not just at the end when the PCB is fully completed. So the first thing that comes to mind is, can we do the simulation in the same environment as we do the mechanical design? And the answer is yes. So certain tools like SimCenter 3D allow for a single unified environment where you can do the mechanical design, the meshing, create the boundary conditions, and do the post-processing. And since you're in a single environment, well, first of all, there's no file transfer. And it really facilitates the design exploration and the optimization that you can do because there's no file transfer. Now, how can we optimize and make this loop as efficient as possible? Well, first of all, similar to CAD, to ECAD, MCAD integration, there's the performance and the efficiency of this process. So that's why in our solution we use 2D multi-layer shell approach. So if you start meshing your PCB with 3D elements, with all the details of the copper traces, this can be a very manual and time-consuming process. So the 2D multi-layer shell approach allows you from CAD to automate the simulation preparation. From this slide, you start from ECAD, translate your design on the mechanical side, as we saw ideally with the IDX format. Then, once you're in the mechanical environment and this unified environment, you can take into account the board conductivity by automatically creating, with a trace mapping approach, the spatially varying conductivity images of the board for all the different layers, but also for the true plane conductivities. In other words, the vias. So the board conductivity is taken into account automatically. For the components, we can automatically generate lump representation of all the components with different JEDEC models, 1 resistor, 2 resistors, based on the level of details you're looking for. And then after, you automatically create this thermal flow model by meshing the boards, meshing the components, creating the simulation objects and all the boundary conditions that are required for your simulation. In my presentation last year at the NAFEM World Congress, we compared this approach with the 3D detailed approach, and the conclusion was that we could get the same level of precision within the 1 degree Celsius if your parameters are set correctly. The advantages of this approach, of the multi-layer shell approach, are multiple, but I would really like to bring your attention on two. First of all, the performance. By this approach, it can take minutes instead of hours when compared to the detailed 3D meshing approach, and based on the level of complexity to generate this model. So you're not wasting time doing manual work, and since you have a performant process, now you can promote the simulation during the design process. So since it only takes you a few minutes to generate your simulation models, you can run it more often earlier in the design process. So for example, at the component placement, with maybe just an average of the copper distribution per layer, at the pre-routing when you're starting to get some copper content, and then at the end for the full routing, and more often based on the different design iterations. So the performance and simplicity of this approach combined with the precision allows you to really promote the simulation process earlier and benefit the designers of your results. The big second advantage is the CAD associativity. As I mentioned before, we're in a single unified environment in this case. So what that means is that the FEM and the CAD and the simulation objects are associated together. So if we move one of the components on the mechanical domain, the FEM and your objects on the simulation side will also move. Think about it. For the components, if you combine this with the IDX incremental changes, a change from ECAD can be propagated to the simulation in no time. And same thing for the board. If you get a new PCB stack, then you can decide, okay, I want to update certain layers because the other ones didn't change, for example. So this associativity combined with the performance makes it very strong. Looking back at our optimized ECAD-MCAD process, to which we added the CAE aspect for thermal analysis, here's how the optimization looks like at this point. We still have ECAD on the left, MCAD in the middle, but now it's actually CAE as well with our unified environment. So the file transfer is still IDX. We still have the design rule checks to optimize the electronic to mechanical collaboration. But then we have between MCAD and CAE no file transfer, so full synchronization of data from MCAD. And then what's very interesting is that as you get your simulation results and you'd like to optimize the temperature distribution, you can reuse the design rule check engine to validate your different what-if scenarios. So if I move this IC at this certain place, if I move this component there, if I change the board or the mounting hole locations, I can make sure that I don't violate any rules that would be on the ECAD side. So still really optimizing the ECAD, MCAD, CAE collaboration in this case. So now let's go to our last topic, the structural analysis. And in this case, since we're discussing miniaturization of electronics, we'll discuss high density packaging, which are required to address those small form factors. So the ball grid array packages enable closer placement of pins for ICs with hundreds of pins, right? But the difficulty with those packages is that it requires an advanced surface mount process. So first of all, the reflow profile needs to be optimized. And establishing a reflow profile is not easy. You may need to make sure that the minimum reflow temperature is reached to reflow the larger components, and at the same time, the temperature does not exceed the threshold temperature that might damage the smaller heat-sensitive components. So the optimal profile must take into account the solder paste, the flux used, the size of the board, the density of the components on the board, and the mix between small and smaller, lighter components, right? So this is very difficult and time-consuming to find. So you're gonna have to use thermocouples at multiple locations on the board and do multiple trials to get your profile right. And that's just for the reflow. If everything goes well, you're good, but the inspection is difficult. You're gonna need an X-ray machine or something like this. It cannot be manual inspection with these high number of connections. Ideally, you have an in-circuit testing that's very precise and developed that can help you with this. And as we can see from the picture here, the rework is almost impossible. Most likely, you're going to have to throw out the components and add a new one. So it's very important whether you are at the assembly stage with the different processes for the fabrication and assembly of your board, or whether you're in the field, solder failure can be induced by repeated thermal cycling for these components. So when it comes to PCB design, there can be multiple sources of component models. You have the symbols for the schematic, you have the 2D footprints that are used on the electronic side, you have the 3D models, you have the thermal component models, so it could be a compact thermal models, it could be the JEDEC resistor models. You also have structural component models that you need to use. And before going there, it's important to have an accurate representation of the 3D models. And when it comes to ECAD and CAD collaboration, sometimes ECAD can have different 3D models than MCAD. So 3D model exchange between ECAD and MCAD. Why is this important? So first of all, you need consistent and accurate ECAD and MCAD libraries for your design. You need to have the same geometries, you need to have the same orientation of the 3D model with regards to the footprint. And this needs to be synchronized for all your library. Now, generally, approximately 10% of the total PCB design effort is spent on library, and library errors are costly and difficult to catch. In this case, we decided to develop a tool that can exchange 3D models between your electronic library and your mechanical library. So this way, when you come to the simulation side and you need to have an accurate representation of your 3D model, you can be sure that the 3D model is actually the same one that's used between all the different domains. Just like on the thermal simulation side, another very important aspect to optimize your workflow is the associativity. The associativity of the FEM to the CAD part. When you create your different mesh for the die, for the package, the mold, the substrate, the ball grid array, you can associate the FEM to the part file, and when the configuration of your CAD, so again, going from an IDX file, coming from another change from the mechanical designer, you can update your FEM and your simulation environment to reflect those changes. Our optimized ECAD MCAD CAE analysis for the structural is getting very robust. We still have the IDX and the design rule check engine. We now added the 3D model exchange to make sure that the representation we use for structural analysis is accurate and the same between the different domains. The synchronization data from MCAD works. The CAD associativity to the mesh is kept, whether you're doing this thermal and the structural analysis. And also, from the structural side, same thing. You can validate and simulate your changes if you see that there's too much deformation where you place the IC on the board. You can make sure that the new location where you want to place it doesn't violate any design rules coming from ECAD. So in conclusion, we looked at how to optimize a PCB design process by enhancing the collaboration between electronics, mechanical, and the simulation domains. So looking back at the initial challenges, the multi-physics involvement, multiple applications, the processes taking too long because of the large data files to transfer, and the difficulty in sharing data across the departments, well, now what we get is more productivity, since we only have a single data exchange and incremental changes. We have more realism from the PCB substrate, from the component modeling that can be reused from one domain to the other. What's very important as well is the continuity. So again, going back to the incremental changes where you don't have to restart from scratch your simulation, and the CAD associativity that's key there. So the mechanical and the simulation domain don't have to be in different tools, and this allows us to not use more data file to transfer the information. And finally, the exploration. By having an efficient and performant process, the analysis can be conducted sooner in the design process. So again, component placement, pre-routing, routing, and you can use the design rules validation to constrain your exploration. So if you're trying different options to optimize your thermal response or your structural analysis, the design rules can help you in being more efficient when you're trying out all those different what-if scenarios. So at the end, what you get, innovative designs, higher quality products, lower development costs, and faster time to market. So thank you very much for listening today, and don't hesitate to contact me if you have any questions. Please reach out at the email address shown on the presentation. Thank you very much.